I made a mistake on the last question we covered before on the previous lecture, that is a week ago. I did the wrong graph because, well, for cosine 2t, we have a period of 2 pi over b, which is 2, which is a period of pi. So that means the graph of cosine, by the time it gets to 2 pi, would have completed how many periods? 2, right? And I just did a half of the period. So that's 1 and, well, that's 1. And let me do this better. And 2. All right. Open circle here. So that's actually the correct graph to the equation. I mean, to the of the function. The rest of the problem, it's still correct. Okay, guys. Well, let's have a look at one more example. So let's consider the function f of t equals to t minus 3 u sub 2 of t, which is the same as saying u of t minus 2 minus t minus 2 u sub t minus 3. Well, here we have a little problem with this heaviside function here because do you see the translation at 2? But we have a shifting of negative 3, which does not coincide here, all right? Also, here we have a jump discontinuity at 3, but we have a shifting at negative 2. Well, that's 2 essentially, 2 units to the right. So we need to do the make your wish come true a couple times in here, right? However, we're going to graph the function first, which is going to be a little bit tricky. Well, so the first term you see, it's a step function, isn't it? So that means in front of it, essentially you have a 0. I mean, in an invisible 0, there's nothing. So that means this function is equal to 0. So we start with a signal of 0, and then we turn it off when after at t equals to 2. So we're going to have here an open circle at 2. And then what happens? Well, we have the function t minus 3, which is, well, 1, 2, 3, which is essentially this diagonal line, right? However, that diagonal line is going to go only between 2 and 3 because at 3 we already have another function. Well, so between 2 and 3, which is over here, okay, that's going to be the diagonal line. Uh, y equals to t minus 3. Okay, the last part of the graph, that's where things are going to get a little tricky because check this out. What do we start with? We started with a 0, and then at 2, that 0 turns off, and we turn on the diagonal line t minus 3. And then what happens at 3? At t minus 3, okay, at t minus 3, we turn off. Okay, let me do that on the side. We turn off. We turn off. Whoops. So that's on minus off. What do we turn off? We turn off this t minus 3. Okay, and what do we turn on? Well, okay, we don't know what are we going to turn on at this point. However, we already have the result we end up with. So t minus 2, which is t minus 2. So the question here, t minus 2 minus t minus 3, that's going to give us, so essentially we turn this off to turn this on. All right, so that is t minus 2 minus t minus, or rather plus 3, that equals to 1. Or actually, yeah, that's supposed to be a 1, all right? So, okay, so that'll be equal to 1. Okay, oh, with a different color. Okay, so, and that goes on forever in this case, right? Okay, well, so let's see. Let's find the Laplace transform for this one again. We wish we had a minus 2. So f of t equals to t minus 2 plus 2, and then don't forget the minus 3. u at t will actually use up, let me use the other notation, use up 2 of t to save some space, minus, we wish we had a shifting at minus 3. Well, so t minus 3 plus 3, and then don't forget the 2, u of 3 of t. Use of 3 of t. Okay, so let's combine what we care. Okay, so I'm going to highlight the t minus 2, and I'm going to highlight the t minus 3. And then I will, what is that? I will combine everything else. So f of t equals to t minus 2 minus 1 use of 2 of t minus t minus 3. 3 minus 2, is that equal to 1 use of 3 of t? Okay, so again, let me highlight the t minus 2, the t minus 3, because I will distribute u with its translation, and then with a constant doesn't matter that much for now, with the correct shifting, and then with a constant 1. The rest, let's just find the transform of it, right? So let's see. So f of t equals to t minus 2 with its transform u sub 2 of t minus simply u sub 2 of t minus t minus 3 u sub 3 of t minus u sub 3 of t. Okay? And well, we're ready to find the transform of every single term right here. Well, here we're finding the transform essentially of just to remember the pretend we don't have everything, anything, all of this. I mean, just find the Laplace transform of t, which is that 1 over s squared. All right. But because we have this translation with 2 units, so we do, okay, this is f of s equals 1 over s squared e to the negative 2s. All right. And then the transform of the unit step itself is simply e to the negative 2s over s minus, actually. And then minus, again, another, pretend you don't have all of this, find the transform of t, which is 1 over s squared, but because of the translation, that is 1 over s squared e to the negative 3s. And then minus another, what is that? That's e to the negative 3s over s. And that is our transform. All right? Yes.
I don't see it too much, but could you like point out each like which part of the Laplace transform is like connected to f of t? Like
So, yes, it's so we have 4 terms, 1, 2, 3, and 4. So this would be this guy, that guy, that guy, and that guy. All right. Okay, so we're done finding transforms of unit step functions. Yes, we did quite a number of exercises of examples because these are a bit tricky to do, a bit tricky to grasp. Okay, now let's do the inverse transform using the second translation theorem. We started this section right here. We talked about how we were going to find the transform. Well, for the first translation theorem, we multiplied, or rather, we had the transform of a function multiplied by an exponential factor that actually shifts whatever s minus a in accordance with the coefficient of the exponential. So in that case, we did a translation on the s-axis. Now we're going to do the reverse. So we're going to find the inverse transform of a function of s. Then the shifting is going to do after the inverse transform on the t variable. That's why we call it translation on the t-axis. All right? Well, so first of all, simply, okay, ignore this exponential if you want. Okay, let me highlight just to ignore for a while. What's the inverse of 1 over s minus 4? Okay, well, that's actually comes from an exponential, right? E to the, e to the, what is that? 4, all right, e to the 4t, right? Okay, I'm going to open parentheses and t. I'm going to close parentheses. I'll show you why. Because in this case, what are we doing? We'll find the inverse transform of using the second translation theorem. Look at the exponential. So here, This corresponds, this right here correspond. Okay, let me actually highlight better. Let me do a better highlighting here. Okay, so here, for every exponential factor you have in your function of s, when you find the inverse, that corresponds to a unit step function factor with the same translation. Okay, so that means I'm going to write u of t minus 2, all right? However, yes, it was fairly easy to find the inverse transform of 1 over s minus 4. That's the exponential. What does the theorem tells us? Whatever function of s that we find the inverse of, yes, come up with a function of t, but do the same translation. So in this case, t minus 2, all right? And that is the inverse transform. Remember when we were preparing these functions to be transformed, all right? We needed to make sure that whatever it was being multiplied by a unit step function, that function must have the same translation as a unit step function. Well, the end result, it's the same. Go back to a prepared function to find its transform of and get the same result. Now, you find the transform of this function using second translation, you're going to get the same result. Again, what are we going to do? Okay, wouldn't we pretend that we don't have the translations? What's the transform of e to the 4t? Isn't that e to the s minus 4? But because of the translation, on pretending, okay, then we multiply by e to negative s, e to the negative 2s. So, same. All right. Inverse transform of, okay, so inverse transform of s over s squared plus 9. Ignore the exponential. Isn't the cosine of 3t? Okay, so that is cosine 3t, but because this is translated, that is u of t minus pi over 2. All right. However, hold on. Let me make some room here. And let me do some translation. So in reality, this would be bracket, parentheses, t minus pi over 2. All right? And that'll be our transform, our original function, back to a function of t. Do you see how they both factors, they have the same translation, you know? Okay, so what next one? Okay, guys, the next one, it's an interesting combination of the two translation theorems in the same exercise. All right, because well, the denominator. Have a look at the denominator. Can you factor the trinomial in the denominator? Factors of 2 that add up to negative 2? There's no way, right? Well, so if you use the what's it called? The quadratic formula, most likely we're going to get either irrational numbers or complex numbers. So, well, that means I'm going to complete the square for this guy. Okay, so let's see. S squared minus 2s plus blank plus 2 minus blank. So that is negative 2 divided by 2 quantity squared, which is 1. That means s squared minus 2s plus 1, okay, plus 1, and this is s minus 1 squared plus 1. All right, so what are we going to do here? Okay, so 3s plus 2 divided by s minus 1 squared plus 1, okay? And then I'm going to multiply by e to the negative 2s, okay? Let's keep going about this one. All right, so this, if you observe the denominator here, that actually is going to require the first translation theorem, all right? In its inverse form. Okay, but here's the thing. Do you see the s right here? It's just an s multiplied by 3. What do we wish right here? Don't we wish this were an s minus 1? Right? We can make our wish come true, of course, right? So 3 times s minus 1 plus 1 plus 2 outside s minus 1 squared plus 1 e to the negative 2s. All right. Okay, so let's group. Okay, let me highlight again the same way I did it before. Let me highlight what I care as a one term. S minus, yeah, you see three terms there. However, the s minus one, I'm going to take it as one term because it actually coincides with the shifting in the denominator. Okay, so this is equal to, I'm going to distribute 3s minus 1, 3 times 1, that's plus 3, plus 2, divided by s minus 1 squared plus 1 e to the negative 2s. Okay? So, what's next? I'm going to do 3s minus 1 plus 5 divided by s minus 1 squared plus 1 e to the negative 2s. And from here, guys, I'm going to split this into two fractions. Actually, do you see the s minus 1? That's going to give us the cosine when we invert it. And the 5 over that one is going to give us the sine. So we're going to end up with two of them. All right. Okay. How is that going to work? Okay. Number one, here it is. We want, well, actually, I was supposed to write the inverse transform symbol all the way. Okay, but I forgot. All right, so inverse transform of, on the one hand, 3 times s minus 1 over s minus 1 squared plus 1, okay, e to the negative 2s. And then I'm going to take out the 5 outside of the factor. Okay, let me make more room so it doesn't look like kind of blended here. Plus 5 times the inverse transform of uh, 1 over s minus 1 squared plus 1 times e to the negative 2s. Okay? To this point, I mean, I'm putting this into two terms. Well, what's going to happen later? Okay, remember the treatment we did to the inverse transform when we had this first translation theorem. So I'm going to, in a way, simplify the notation by saying that this is the inverse transform. Actually, you know what? I should have taken these three outside as well. I'm going to take it 3 Laplace inverse of, I'm going to say s over s squared plus 1, where s goes to s minus 1, e to the negative 2s, plus 5 times the inverse transform of, same, 1 over s, or similar, 1 over s squared plus 1, where s goes to s minus 1, e to the negative 2s. All right? Okay, so at this point we're ready to find the inverse transform. Do you see them? These are simply what are they? Cosine in the first one and sine in the second one. Okay, so this is okay. Check this out. This will be 3 times cosine of, wait. 3 e to the, and then cosine of t. Okay, I'm gonna close parentheses, and then what else? Some unit step function at, where's the 2? Yeah, at 2, right? Plus 5 times e to the something sine of t minus, in this case, minus 2. And guys, we would say the following, wouldn't we? Okay, so here s minus 1 goes to simply t, isn't it? When we do the inverse transform using the first translation theorem. But guys, everything you see back to the world of t has to be shifted as well. All right. So not just the inverse transform that got us to cosine and sine. If we had that factor that yielded that exponential factor, that factor has to be shifted as well. So everything back in the world of t. Wait, this is supposed to be a u, well, t minus 2, u of t minus 2. All right. All right, guys. So that was the final answer to this exercise. Let's have a look at some differential equations. So, solving differential equations where the forcing functions involved are in our unit step function somehow involved, or heaviside function. Okay, so what do we have? Y double prime plus y plus equals to some function f of t with conditions y of 0 equals to 0 and y prime of 0 also equal to 0. Okay, so here they're telling us that the function equals to 1 between 2 inclusive and 8 exclusive. So that is between 2 solid exclusive and it's 0 everywhere else. All right. So that's actually our function here. All right.
This is one. Okay.
One. Yes, you're right. You're right. That's one. Let me. Thank you. Thank you. Yeah. Yeah. I was looking at this too. I think that's why that's what I thought about. Okay. So let's write this as a piecewise function. G of t equals to that is one. Essentially, that's one between uh well 0 between 0 and 2, and then 1 between 2 and 8, and 0 again between, what is that? For t greater than or equal to 8. All right? So, what about it? So, let's see. So, let's find the Laplace transform of the second derivative plus the Laplace transform of y equals, well, actually, hold on. Before taking any Laplace transforms, okay, let me save this for later. We need to express this as a heaviside function. I was kind of jumping ahead. I don't know why. Okay, so what do we have here? So we have a function g of t, right? I mean, this is f of t, not g. I don't know why I wrote it g. F of t. So f of t starts at 0, okay? And then there's a gain of 1. So plus 1 times u, what is that? T minus 2. And then minus, we have a loss of 1 unit, minus 1, u of t minus 3. Oh, wait, minus 8. All right? So that heaviside function, well, let me simplify this one. Well, let me write it down here. So that is Laplace transform of u of t minus 2 minus u of t minus 8. Okay? So the transform for the second derivative, well, what was that? Is that y of s squared, y of s, minus y of s, or rather y of sy of 0 minus y prime of 0, right? So that is the Laplace transform of the second derivative, isn't it? Now, the Laplace transform of y is simply y of s. There's nothing else other than that. And well, here, the Laplace transform of u of t minus 2, it will be e to the negative 2s over s minus e to the negative 8s over s. All right? So we have transformed the equation. Let me move it up here. Now let's substitute with the initial conditions, which in this case, they are both 0, right? Because y of 0 equals to 0. This goes to 0. And y prime of 0 equals to 0 as well. So we would end up with a relatively nice differential equation here. Okay, so this is s squared y of s plus y of s equals to e to the negative 2s over s minus e to the negative 8s over s, okay? The rest of the problem is an algebra problem. I mean, well, not the rest of the problem. So factor y of s that times s squared plus 1 equals e to the negative 2s over s minus e to the negative 8s over s. All right? Now, simplifying, uh, no, I don't want this. Simplifying, or rather solving for y of s, which is essentially multiplying both sides by 1 over s squared plus 1, okay, that's going to give us the following. Multiplying across, well, here we cancel out e to the negative 2s over s times s squared plus 1, okay, minus e to the negative a s over s squared, I mean s times s squared plus 1. All right? Well, so it seems like a big problem because of the partial fraction decomposition. And in fact, all we have to do is simply one. Okay, let me actually rewrite this one, so you can see what I'm talking about. Y of s equals, how about 1 over s times s squared plus 1 e to the negative 2s minus 1 over s times s squared plus 1 e to the negative 8s. Okay? Well, do you see the rational function multiplying both of the exponential function? It's the same, so just need to work with one. Okay, so how is that going to work? Well, we have 1 over s times s squared plus 1, which on the one hand, there's a linear factor that is a over s plus bs plus c over s squared plus 1. All right. And guys, I'm going to skip the partial fraction decomposition. You guys are masters of partial fractions at this point, right? So you know what we're talking about over here. Okay. So these yields are not equal. It's equal actually. Um, this is okay. So this is um, A equals to 1 over s plus 1 times s plus c, which is 0 over s squared plus 1, which is 1 over s plus s over s squared plus 1. All right? Okay, guys, now that we are at this point, can you find the inverse transform 1 over s? So let me use a different color for this. What I'm doing here is to prepare to find the inverse overall. All right? So well, not yet. Actually, let me do the following first. I will do y of s equals to 1 over s plus s over s squared plus 1 times e to the negative 2s minus 1 over s plus, what is that? Another 1 over s squared plus 1, but this time e to the negative 8x, negative 8s, not x, s. Okay, well, what's the inverse transform of 1 over s? Isn't that what is that? Isn't that just 1? Okay, so y of t, finally finding the inverse. The inverse of 1 over s is 1. Okay, plus what's the inverse transform of s over s squared plus 1 again? Cosine. Cosine of open parentheses. Well, let's hold on. Okay, and that times close parentheses. And well, because we're being multiplied this term, or these factors rather, this factor by an exponential with that means u of t minus 2. So t minus 2 here as well. All right? Minus 1, actually in bracket 1, the same, plus cosine of t, but the shifting goes at a, right? And guys, this is our solution to the differential equation. Okay. And yes, I skipped the partial fraction decomposition because I want to do another example. I also want to move on to through the topics. You guys know how to work partial fractions, all right? Okay. Example number 13. One more, and we call it two for this section. All right, so we have y double prime, okay, y double prime plus 3y prime plus 2y equals some function g of t. Well, actually, this should have been a function f because of the graph. That's f, not g. All right, with initial conditions, y of 0 equals to 0 and y prime of 0 equals to 1. I mean, when all are zeros, I mean, that's a nicer problem. But well, here we have a 1, so it's not going to be that bad, right? Okay, so that's also f here. All right, so I don't want this. Okay, there we go. So let's write the heaviside function here. So why do we start with our function f of t? We start with a 1, isn't it? And then we have a loss of 1 unit, right? So that means minus u of t. Where does that occur? Isn't that at 1? So that means u of t minus 1, the shifting to the right. So just maybe you notice this, guys. We never see positive numbers here because the negative shiftings imply shiftings to the right. We don't care about shiftings to the left because we're not looking at negative times. We're looking at times between 0 and infinity. We don't want to go back in time, right? Okay. So what's the next? Okay, so let's rewrite the equation y double prime plus 3y prime plus 2y equals to 1 minus u of t minus 1. Okay, so let's find the transform of all of this. Okay, so that is y double prime of s or s, wait, s squared y of s minus s y of 0 minus y prime of 0. So that is the transform of the second derivative. Well, actually, I think I'm going to need extra space. So I'm going to go below the graph. All right. Now, plus 3 times the transform of the derivative, which is y of s minus y of 0, okay, minus y of 0, and the transform of 2y, that is plus 2 times y of s. And then here the transform of 1 is in that 1 over s. And then the transform of the unit step function minus e to the negative s over s. Okay. And we have transformed our equation. Okay, yes. Again, initial conditions. Y of 0 equals to 0. So this is going to go to 0. This is going to go to 0 as well. And y prime of 0 rather equals to 1. All right. Okay, let's write what are we going to be left with. So that'll be so s squared y of s minus 1 plus 3s y of s. Okay, this is going to go to 0. We don't need to write that one. Plus 2y of s. Okay, equals 1 over s minus e to the negative s over s. All right. Again, it's to isolate y of s, solve it algebraically, and then find the inverse transform. Okay, so that's y of s squared plus 3s. Oh, wait. Actually, no, not yet. Let me add 1 to both sides. All right. And this will be s squared. Okay, finally, I'm going to factor. Okay, let me factor y of s finally. Y of s times s squared plus 3s plus 2. Okay, and then equals to, okay, on the side. Let me take a side trip here. Let me add 1 plus 1 over s. Divide by 1, multiply numerator denominator by s. This would be s plus 1 over s. All right. You guys agree with this? Because you guys want to have simplified fractions to better. find the inverses of. Okay, so this would be equal to s plus 1 over s plus, or rather, minus e to the negative s over s. Okay, again, divide both sides by the trinomial, or even better, multiply by the reciprocal. And that's going to give us the following. Y of s equals to s plus 1 over s times s squared plus 3s plus 2 minus e to the negative s times s squared plus 3s plus 2. Okay, so uh, yeah, so here in this case, we would have to do two partial fraction decompositions. Actually, we can simplify the first one because if we, okay, check this out. If we, y of s equals to s plus 1 divided by s, factors of 2 that add up to 3, are they s plus 1, s plus 2? And check what happens. The number of partial fractions reduce. So guys, when you're finding the inverse transform to solve a difficulty, if you end up with more than one fraction, try to factor all the way, because in some cases you may end up actually simplifying a lot. Minus e to the negative s, s same, s plus 1, s plus 2. But in this case, there's nothing to actually simplify. So what do we do next? Y of s equals 1 over s plus 2, I mean s times s plus 2, minus e to the negative s. This time I put the exponential factor in the front. It doesn't matter, really. Um, and this is times 1 over s times s plus 1, s plus 2. Okay? Well, here again, I'm going to skip the partial fraction. So partial fraction decomposition, that equals uh, 1 half, yeah, 1 half over s plus 1 half, I mean, no, minus s plus 1 minus e to the negative s. That'll be 1 half over s plus 1 half over s plus 2 minus 1 over s plus 1. Okay? Yeah, that's after maybe 2 pages of partial fraction decomposition. Well, maybe not 2 pages, maybe 1 page. Maybe 1 page that actually covers for both problems here. Okay, I mean, guys. Okay, here. Okay, be careful here because the first two terms do not have any exponential factor. All right. Yes.
Uh, 1/2 over s minus 1/2 over s plus 2.
Plus 2. Thank you. Plus 2. You're right. Thank you. Okay, so notice in this case, they don't have an associated translation because these two are not being multiplied by any exponential factor. All right, so finding the inverse of y of t, the inverse of a number over s is just a number, isn't it? The number minus 1 half e to the negative 2s. All right, is that what it is? And then, okay. Oh, wait, not s, 2t minus, okay, 1 half plus 1 half e to the negative 2 times t minus something minus 1, which is simply e times e to the negative t minus something. And then all of this multiplied by a unit step function, u of t minus 1. Shift by minus 1, shift by minus 1. All right. and make some room here and call this our final answer.
Yes.
That's it's all right. It's all right. I mean, yeah. Okay, yeah. What's up?